Kristen Atchison here, and we're going to do a hand calculation for the t-test for two related samples. So here's our practice problem. Again, the best thing you can do is to practice it yourself, and then try it yourself. Pause the video on the screen, practice it yourself, do the t-test, do the hypotheses, cutoffs, make a decision, APA statement, all of that, and then go back and watch the video and check. Or if you get stuck, go and watch the video and check. So the best thing to do is to try and do it yourself first. So please do that. I'll wait. Okay, for those of you still here, a researcher in behavioral medicine believes that stress often alters asthma symptoms for people who suffer from this respiratory disorder. Because of the suspected role of stress, she decides to examine the effect of relaxation training on the severity of asthma symptoms. A sample of 5 patients participate in the study. A week before treatment, the investigator records the severity of their symptoms by measuring the dose of medicine needed for an asthma attack. The patients then receive relaxation treatment. For the week following training, the researcher again records the doses of medication to each patient. Does relaxation training alter the severity of the symptoms? Okay, so that's the majority of the information we need in here. It's telling us we're going to do this t-test at 0.05. Because it says alter, we know that this is a two-tailed test. It just says, is there a change? It doesn't say, does it make it better? Does it say it makes it worse? It just says alter. It's just a change, right? It says we have 5 patients, so our N is equal to 5. And that's the information we need to pull out, okay, from the practice problem. So our research hypothesis, patients who underwent relaxation training will have a change in medication doses. Again, this is our research hypothesis. Or mu1 is not equal to mu2. Again, this is just telling us that there is some sort of change. This is, again, about a two-tailed test because it's just saying that they're not equal. It doesn't say that they get bigger or they smaller. They're just not equal. The null hypothesis, patients who underwent relaxation training will have no change in medication doses, and mu1 is equal to mu2. Again, this is just telling us there is. So this is that there is change, and this is that there is no change. Okay, so that they're going to be the same. Okay, so our comparison distribution, we're going to compare it to a t-distribution with a degrees of freedom of 4. We do that because, remember, we had a subject size of 5. So 5 minus 1 is equal to 4. And we're going to compare this against the idea of no change, which, again, is equal to 0. So we're always comparing against the idea of no difference. And remember, that's that second part of that numerator in our t-statistic formula. So remember, the absolute first thing that you have to do in calculating a repeated measures t-test or a related samples t-test is the difference scores, okay? The only thing that we're going to use this raw data for is for difference scores, okay? So 9 minus 4 is 5. 4 minus 1 is 3. And 0 and 4 and 4, okay? Now we're going to add all those up, divide by 5, and when we do that, we get a mean difference of 3.2. Now that we've done this, we do not need this data for anything else. We can just ignore it, pretend it never happened. Only these new difference scores are what we're going to use to calculate our statistic. The rest of it, we will not use in any way, shape, or form ever again, okay? So the only thing that you use this raw data for is to calculate those difference scores. So we have our difference. Again, this is just that way to do the table. I've just added this column that has the mean. So 5 minus 3.2 is equal to 1.8. 3 minus 3.2 is equal to negative 0.02. 3.2. And I just added that mean column so you could see exactly what I was doing. Okay, now remember we're going to square these, right? So we'll square this value And we get, so just square each one. And it's the sum of the squares. So we're just going to add all these together, which is equal to 14.80. Okay, so that's our sums of squared for the difference scores. Again, we did not calculate sums of squares using that raw data. We do not calculate sums of squares using that raw data. That is for an independent means t-test. These are not independent means. So we have to do this difference score and then the sums of squared, which actually saves you work. You only have to do one sums of squared instead of two. So it's a really nice option. Okay, so now that we have that sums of square difference scores, we can estimate the variance. So I've just copied that information that we had from the previous slides. Again, both of these formulas are absolutely the same. The only difference is this one has the degrees of freedom formula written in it instead of saying degrees of freedom. Other than that, they're the exact same formula. Okay, so what we're going to do is we're going to take, we're saying s squared is equal to sums of squared. This is that formula that's tattooed on my forehead, right? Is equal to 14.8 divided by 4. When we do that math, we get 3.17. And so 3.17 is our estimate of the variance for the population. Remember, we're estimating this because we don't know the actual variance for the population. We're estimating it based on our sample size, right? That's where it's getting its name, inferential statistics. Okay? Because we're making inferences. Okay, so now that we have that estimate of the population variance, we need to estimate the variance for the distribution of means. We need the estimated standard error, okay? And so that formula is that. So we're going to take our 3.7 that we got on the previous slide. We're going to take our 5 that we know for what our sample size is, and we're going to get 0.74, okay? Now that we have this estimated standard distribution of means, we got to take it one step further and get the standard deviation. So what does that mean we have to do? All that means we got to do is take the square root of it, right? So we had 0.74 is equal to 0.74 is what we got on the previous slide. So we'll take the square root of that. Add those differences so we know what we're talking about. The square root of 0.74 is equal to 0.86. So this is the denominator of our t-statistic. Okay, so our cutoff, remember we said it's a two-tailed test because this test the description just said that they were looking that it was going to alter the severity of the asthma symptoms. Using a t-distribution table, looking at the alpha of 0.05, which again was given to us, we have degrees of freedom 4 because remember we had 5 subjects in the study. Our cutoff is 2.776, okay? This is what we're going to look at is this 2.776. So, and this is going to be plus or minus because it is in, it's a two-tailed test, right? So we're going to look at this value on both sides. And again, we split that, and so this is what it ends up looking like, okay? So we're going to say anything that's in these teal areas, any value that's in either one of those teal areas, we'll be able to reject the null. If it's not in those teal areas, if it's in the white areas, we're going to fail to reject the null. This is how we did that. It was a two-tailed test. We had degrees of freedom 4. There's our 2.76. Now you can go ahead and write on your t-table that if you're over here, it's going to be plus or minus, okay? So in this area here, it's going to be plus and minus. And here, it's going to be plus or minus, okay? Depending on which one it is. So now let's do that t-statistic. So our mean difference was 3.2. Minus the idea of no change, right? Because that's what we're comparing it against, divided by that estimated standard error of the mean difference scores. And we get, when we calculate that bad boy out, a t-value of 3.72. So that sample is in the critical region. Remember we said it was like 2.76 something. So if it was in here, well, our 3.72 is in that area. So we're able to reject the null and support the research hypothesis. In the two-tailed test, the research hypothesis was supported. It would be better to write out what that research hypothesis it was, that the relaxation treatment would altered the severity of asthma symptoms. And then again, we have our APA statement here. I went ahead and already calculated this effect size. Again, when you reject the null, you have to have a measure of effect size in your APA statement. If you had failed to reject the null, so if this was P is greater than 0.05, or this was not significant, then you don't need a measure of effect size because you have no effect, right? But because we did reject the null here, we do need a measure of effect size. You could also do the R squared. Either one is fine. So both of those are calculated there. For R squared, remember, you're going to always want to talk about that in terms of a percentage because it's the percentage of the variance that's explained by the effect.